So, hello everybody and welcome. Today we have Franz from Leiden talking to us. He says he's got a lot of slides, so to keep the introduction short. So with that, I give you Franz.
Thank you, Rob. The only thing, I mean, I have too many slides, which you'll notice. The only thing I hope is that my voice will keep on, but let's see. So I don't even have time just to go through all the words in the title. But I invite you to look at this movie of our own planet Earth. It is my goal in life, and I realize this will take, I don't know, 30, 40 years, to see signals like we see in this movie, but then for some planet around a nearby star that may look somewhat like Earth and has signs of life. But then all this signal will be compressed down to 1 pixel. So that means that the amount of light will go up and down as the planet orbits the star. We might see signs of the starlight reflecting off liquid water, maybe liquid water clouds, which would already be nice. Signs of continents, therefore, and maybe some of the green stuff that grows on some of these continents. Some oxygen in the air, so really signs of life. And realizing that this may take pretty much the remainder of my career. In the meantime, also my focus has literally shifted more and more towards our own planet for astronomy reasons. I mean, if we want to find signs of life elsewhere in the universe, we'd better train on the one planet that we know harbors life, this one. But it also turns out that our own planet is kind of interesting by itself. So I'll go through a number of projects, which I obviously do not do by myself. So this is on behalf of our still ever-growing group in Leiden. And that group works on kind of a spectrum of different things. So mostly today I'll be talking about optical instrumentation for high contrast imaging. We do a whole lot in exoplanet observations, but I figured just to give you a slightly different taste today, I'll focus mostly on the kind of fundamental technology and not so much on the observational science. But as a spin-off of this, we also do a little bit of astrobiology. My laser is finicky. But we also do a lot of spin-off in atmospheric remote sensing. And we even do crazy stuff like citizens art projects. So I'll do a little sample across the spectrum for this talk. And actually in compiling this talk, I feel a little bit like a dung beetle. This is not because I have to deal with balls of shit during my career so much. In fact, the dung beetle is a polarimetric creature. A lot of what I do has to do with polarization of light, and in fact, because this dung beetle navigates on the blue sky polarization, it detects polarization, and it literally tells where to go with its bowl of food. So it does that during the day. What you may not realize is that the dung beetle is also very much an astronomical creature. So dung beetles have been found to navigate by the polarized light of the moon and even by the orientation of the Milky Way. So I'll try to combine my two sides of the dung beetle. I'll start with my nocturnal side and I'll finish with my dung beetle during the day side. So my nocturnal side is really much about exoplanets. So this talk, I don't know, 25 years or slightly less ago, would have an introduction that we know of 9 planets, because Pluto still counted back then. Right now we have 8 planets in the solar system, more than 4,000 planets around the stars that we know of. And I emphasize that we know of because the majority of these planets were detected only indirectly. We have not yet seen them, but we know they are there. And we do that, as you probably all know, by monitoring the light of the stars that they orbit. The stars pull on the planet, but the planet also pull on the star. That means that the star wobbles, and through the Doppler effect, you can infer the presence of planets. And in that way, we, for instance, just the first star next door, Proxima Centauri, is known to harbor a planet, maybe even a planet that harbors life, and indeed is rocky. So the second way of detecting exoplanets is if the planet happens to cross between the star and us. Of starlight has a little dip, and that comes back periodically, and that allows us to detect planets, or indeed planetary systems, like our southern neighbors and your western neighbors, the Belgians, very proudly named this TRAPPIST system that has 7 of these things coming by, and a few of them may even be habitable. But so with all these observations, we now have a complete zoo of exoplanets, and this to me shows that the universe has more imagination than science fiction writers, because the craziest planetary systems exist. So science fiction figured out planets around binaries, but 7 rocky planets all in a row, Jupiter's being in an orbit where we didn't think they could belong. The craziest planetary systems are out there. But it is very difficult to see them. So if we take an observation of the brightest star in the sky with the best space telescope that we currently have, so this is a Hubble observation of Sirius, this shows how difficult it is to see a planet orbiting this star. If we do see something that's orbiting this star, this little blip in the lower left corner, but that's another star. That's the binary companion of Sirius. If we want to look for planets, we need to go in the middle of all this mess of diffracted light and go a million times fainter than that thing. So that is the challenge that we have. Now I speak of me and mostly also my colleagues, we have movies now of planets orbiting other stars. So this is certainly my favorite movie of the last few years. Here you see the remnants of the light of the star HI 8799. So the light in the middle has been removed with optical tricks and also data analysis. There's still a little mess left over, but in that mess you clearly see 4 planets orbiting this star for the duration of several years, which I think is very cool that we can make movies like this. We literally see it's moving around another star than the sun. In this case, it is, in quotes, relatively easy to do because it's a young star. Therefore, the planet's also young. These are massive Jupiter-like planets that are still contracting, radiating in infrared, and the contrast between the star and the planets is still moderate, of the order of 10,000. If around this star we would like to see a planet like our own Jupiter, we would need to get in this kind of black area in the middle that this instrument cannot do. So the orbit of Jupiter at this distance would be the red circle. If you would like to see an Earth, this is this tiny blue circle way in the middle that we cannot reach yet. So we need to get, we are developing technology that goes closer into the star and at much deeper contrast levels, such that within, let's say, 10-20 years, we can really reach this orbit around this star. Just to provide a metaphor how difficult it is to see Jupiter and Earth around the sun, if the of a star would be Mount Everest. Jupiter would be in visible light 1 billion times fainter, and the Earth would be 10 billion times fainter. So on this scale, Jupiter would be a red blood cell, and the Earth would be a bacteria. And we need to find those with an altimeter on the slopes of Mount Everest. So some of the technology we built is literally bulldozering down part of Mount Everest down to rubble, and then we find blood cells, hopefully sometimes at some point bacteria among the rubble. And if we go to space, we polish Mount Everest down to optical quality. So this is the technology that we want to build, and we are building them. So with so-called coronagraphs, we can manipulate the diffraction halo around stars. The implementation of a coronagraph we're aware of consists of physically blocking the light of the star in a focal plane and then having to deal with the diffraction around that. We do something different. We manipulate the phase of the telescope in the actual pupil plane. So on the upper left you see a phase pattern for a telescope where you have to imagine that the outer radius is the primary mirror, and this would be the shadow of the secondary mirror. And if you apply a particular strange phase pattern like this, the point spread function in logarithmic scale would look something like that. So in this D-shaped region, the light has disappeared and moved to the other side. So in that region, you can start looking for planets. So people have been building this by carving out this landscape on pieces of glass, which is nice, but it has 3 disadvantages. This phase pattern only strictly works at one wavelength. Chromatic. It is very difficult to get the phase pattern very accurate with diamond turning, and maybe a stupid reason, if the planet happens to live on the other side, you have to wait for the sky to rotate, or you have to rotate the whole thing. So years ago, we came up with a solution that allows you to build 2 point spread for the same star and solve all the other issues as well. So what we do is we turn this height landscape into an orientation landscape here. And all these little vectors are liquid crystals. So we built these coronagraphs out of the same stuff that is in your displays of your computer or your cell phone, in which other industries have invested billions and billions already, which will happily adopt for astronomy. So it turns out, if you orient the liquid crystals according to these little arrows, and you split circular polarization, you can do exactly this. So you get the two point spread functions with dark holes on either side. But it also turns out that this liquid crystal pattern doesn't change as a function of wavelength. So this is inherently achromatic. This works very well for all wavelengths at the same time. And with all this modern liquid crystal technology, we can make very, very crazy phase patterns that I will show you. So in practice, we have one of these liquid crystal plates. The light that comes in, we separate in equal amounts of circular polarization. This being a half-wave plate, it flips the circular polarization, and upon doing so, it inscribes a phase. So this is not the classical phase that you know from your optics textbook. This is the so-called geometric phase, or the Poncelet-Berry phase that it imposes on it, and it's strictly achromatic. So this coronagraph that we call the vector apodizing phase plate, because it sits in the pupil plane, every point source in your field will get exactly the same point spread function. So that means if your telescope vibrates, the dark hole will be dark. Contrary to other kinds of coronagraph. We can switch around in the infrared if you want to do so, but particularly because of this liquid crystal technology, we can make this work for like the entire visible range or major chunks of the infrared. So we'll also demonstrate. You can do this for the UV or even the mid-infrared, and the dark holes that you get to these phase patterns are really deep, close in. You have a search space that goes all the way around, and most importantly, it's just a single glass plate with some crystal on. You stick it in a telescope. Doing over the last few years. So this is the first plate that we've manufactured. This is by now 6 years ago or so. So this is an image taken of this glass plate with this particular pattern between cross polarizers, and it looks very, very colorful and nice. But when we stuck it in our lab setup where we have an artificial star, we get two images of the star, and then we crank up the contrast, and this indeed showed that this worked nicely. We also showed that this worked nicely throughout the visible wavelength range. The only thing that the point spread function does is grow with wavelength as diffraction works. So from the lab, we went right away to the telescope. This is an image on sky, so this is not a simulation nor in the lab. This is an actual star on the Magellan 6.5 meter telescope in Chile through the infrared adaptive optics system. And what you see here is two images of the same star with a dark hole on either side, and actually a term in the middle that we can use for reference like astrometry and photometry. And you see that these dark holes are really quite dark. If you blow up the contrast some more, you see that they're not quite dark because the adaptive optics is not perfect, but we can play a little trick where if we want to see a planet here, we can use the information in this dark hole, and we just rotate and subtract it out, and all the stuff is gone. So with that, we could demonstrate that we have a contrast of a few times 10 to the minus 5 in this dark hole. We're currently using this to this turns out to be somewhat more difficult than we thought. Something went wrong here. So upon that, I got a nice little amount of money out of Brussels, where we now take this technology to all these telescopes that you see here, and I'll show you some examples. So my students now regularly have to go to Hawaii and Chile to work with this, and we also had a funny adventure up in Canada. So I'll go through this, and again emphasizing I'm not doing this by myself. I have the pleasure of collaborating with all these fantastic people. So the first one that we installed looked like this. So now the phase patterns are getting slightly more funkier. So again, you see here the pupil of the telescope. In this case, it's the 8-meter Japanese Subaru telescope on Hawaii, where we, in the telescope aperture, print this strange phase pattern. So this is the design. This is the optic as fabricated. And then we installed it in that adaptive optics system. And right away, first light on the camera, it worked beautifully. The data that we got out of their integral field units, what you see in this movie is several things. First of all, the point spread function is shrinking and growing. This is when we go through wavelength in that particular observation. So that makes images for a whole different wavelength at the same time. So you see the point spread function growing from the wavelength at 1 micron all the way up to K-band 2.5 microns. The thing that you see here is this kind of bow tie, focal plane that is only suppressing the amount of light in these bright patches by a factor of 100, otherwise we would kill the detector. And what you see here next, in this, so the dark holes are here and here. In this dark hole, you see a companion that you particularly see very well at the very reddest wavelength. So in a single shot, we already see slightly heavier than planetary mass things. And so this optic works at a quite stupendous wavelength range from 1 to 2.5 microns. So the diffraction efficiency is very close to 100% for that range, and also the transmission of the optic is really nice with a little dip in the K-band. By now we have even introduced a few tricks, because all this light here on the bright side is not useful. Contains information on how well your optics and adaptive optics works. So we now have a control loop that science focal plane tells you how the adaptive optic needs to be corrected to make the dark hole darker. So at every point in the focal plane we can add information to help us build higher contrast observations. Also these spots here can be used for that purpose. So this is another optic that we built. This one is for the Large Binocular Telescope, and in fact there's two similar patterns next. We can use both the apertures, and this is a beautiful looking pattern where we add a grating to split the circular polarization, and we actually add another grating to combine them again to get rid of some leakage effect. And this is the point spread function that goes with this. So on the left, the simulation; on the right, an on-sky image when the seeing was actually very lousy at the LBT. So there's a lot of stuff in the dark hole, but this is to demonstrate that we can also make dark holes that goes all the way around. And to go even crazier than that, this is a similar point spread function with a 360-degree donut dark hole, and now we built an entire Christmas tree of lights around this. And this is also to provide wavefront sensing. So every combination of spots around this carries information about a particular wavefront error. For instance, if you just defocus the camera, this combination of spots here and there tells you it's just a defocus in this direction. You have to so much, and all the other aberrations are fine. So the phase pattern that does this is something crazy like this, but with this liquid crystal technology we can print crazy things like this. So what it looks like in practice, it's just a piece of glass, and in this case we have a bunch of designs printed on a piece of glass that we then stick in an instrument. And in this case we stuck it in this instrument back here that looks like a large washing machine, but it actually contains a 30 centimeter telescope which went on a stratospheric balloon, which is not this balloon. This is the tiny balloon. There's a bigger balloon that takes this to almost 40-kilometer altitude. So this is what I did last summer. So this is the big balloon going up here. You see the little, and this is our telescope assembly. And this experiment was really just to develop and demonstrate technology for doing high contrast imaging in space. So we had quite a number of technical issues, but our coronagraph worked nicely up in space, as we kind of knew it would. So the kind of data that this telescope produces looks like this. So here we have our two dark holes, and a control loop on the adaptive optics that works on these spots to tell what the optical system is doing. So this we now raised our technology readiness level, as it's called in space lingo, and these liquid crystals really work very, very nicely. We can do even crazier things with this. I'll give you two examples. So in addition to coronagraphy, we can now also do interferometry with these liquid crystal things. And what we're doing interferometry with a single telescope is to put a mask on the telescope pupil and just cutting out a few holes on the telescope aperture that produces fringe patterns, which is called sparse aperture masking. Which does mean that you're throwing away a whole lot of light in between these holes. So now with our liquid crystals, so the holes for the sparse aperture masking are the ones here painted yellow. All the segments in between, if you look carefully, you can see that this is the Keck pupil. We multiplex these strange crystal patterns such that we use the light and do more interference with them. So every segment has a very crazy liquid crystal pattern, and then you get point spread functions like this. So here in the middle you get your standard interferometric point spread function, but around it you get a whole spaghetti of fringes as a function of wavelength that adds information to this point spread function. So now we can do interferometry as a function of wavelength using all the light of the Keck observatory, because on the right is an image, first light of a binary that we acquired just a couple of weeks ago. It gets even crazier than that, because we're now building patterns like these psychedelic patterns here on the left to go on the principle of a little space telescope that would look at Alpha Centauri, our neighbor stars. There's 2 of them, and one way of finding planets around these 2 stars is to see if the distance between the 2 stars periodically grows and shrinks by micro-arc seconds. And if you detect that, that means there's a planet either around this one or around this one. So with these crazy patterns, we turn the point spread function of both stars into kind of like darts boards that, when they overlap, provide you this kind of astrometry between the both of them. But these are little side projects at the moment, although one of these now got funded and will fly in a CubeSat even this calendar year. But of course, the telescope that we're really getting excited about is the extremely large telescope. Currently, unfortunately, still an artist impression and not real drone footage. I like this movie because, to scale with the little cars, it really shows you how large this is. I mean, the dome is almost a football stadium, and the mirror will be 39 meters across and built up out of 798 little hexagonal segments that will need to be pieced together. So this is under construction right now in Chile. But I'm a kind of impatient person, so I built one myself. So also this is an artist impression, but it really exists. So there's more than 20 of these all around the world now, and I think you guys should have one in your house, the astronomy. There are 3 instruments that go to this telescope for which we're now developing the technology and the coronagraphs. And MagAO is the first light camera. METIS is the big infrared instrument that you guys are probably involved in as well to some point. And the ultimate planet imager will be EPIX, but that will be 10 years down the road. Something else fun that we did with this telescope side is that we turned the site into an art project. So what we did is, me and the artists that I have in residence, we collected sand from the sites that this telescope we built, and we melted this sand into very big lenses. So we certainly would do astronomy with it, but the artists took these lenses back to the desert and had the desert photograph itself. So you get these beautiful, very abstract-looking pieces of art. And one of the photos that he had to make, of course, was Amazonas, where the ELT will be. So this is currently in my office. Also that as a little aside. So just to give you an overview of where we're going to go with high contrast imaging on the ground and in space in the next, let's say, 20 years. So what I have here is a plot of contrast going all the way down to 10 to the minus 11. Remember, 10 to the minus 9 was red blood cell to Mount Everest as a function of angular separation from the star. So the kind of planets that we can already see, like these HR 8799, they're up here. So they're like 10 to the minus 5, fairly far away from the stars. But if we want to detect cold and old exoplanets in reflected light, we need to get down here. Now, of course, the contrast on this projector is not very great. But if we, this one you see, so most of the habitable zone rocky planets that we want to see, so those are the planets on which we could signs of life. They're down here in this color triangle, and the color code is actually the stellar type. So to detect or to see a planet that may have life, we need to cut into this triangle. So if you have an Earth. There's 2 exceptions, what would be Proxima Centauri b and a potential habitable planet around Alpha Centauri that would be here. Everything else is in this triangle. So with our current instruments like SPHERE, we cut there. If we do some other tricks like polarimetry, we're going down, and now we're trying to upgrade SPHERE, and with an upgraded SPHERE on an 8-meter telescope, we could just barely see Proxima Centauri b. Once we build the ELT, we can go much further in. Is larger, and we have some more technology development. With the ELT, we will be cutting into rocky planets in the habitable zone around M dwarfs. So for the first time, really seeing planets that could have liquid water and therefore life. If you go into space, the contrast that you can attain, I'm not going to explain that, can be much better. So if you have a 4-meter telescope optimized in space, you can start hitting an Earth around a sun-like star at 10 parsec. And if you have a small telescope like 40 centimeters, fully optimized for Alpha Centauri, you could detect those planets. So just to summarize all this spaghetti, with the VLT, we can do Proxima Centauri. The ELT will land about here, cutting into the M dwarfs. To go for Earth around Sun-like stars, we really have to go into space with future space telescopes such as HabEx, and for Alpha Centauri we can do something small. Which also means that this is really exclusive ground-based territory. There will not be 40-meter telescopes in space in our lifetime. So to see these planets, we have to build the ELT. And this is really exclusively accessible from space. So these developments are very complementary. But my interest is not so much in just seeing a planet. I want to characterize it. And to get into that and get you guys involved a little bit, I have this beautiful photo of a rainbow, and there's a kink in this rainbow. Now my question to you is, why is there a kink in this rainbow? And I'll give you a hint. This photo is taken from a boat in the open. The diameter of the drops, that's close, but not quite yet. Sorry?
Salt, rainbow?
Yes, but I think you're cheating because I asked this in another presentation where you were present. But usually, so I'm doing experiment with all the audiences that I talk to. So school children get this way faster than professional audiences. So indeed, here it's raining fresh water, and here you got splash salt water. So that's different refractive index. So the rainbow is at a different angle. So this picture by itself shows you how just from an observation of light from a distance, you can infer what kind of stuff is in the atmosphere. And in fact, a very similar observation of rainbows was used to infer that the clouds of Venus were not fresh water, were not salt water. No, they were 75% solution sulfuric acid water. One other good reason to not go to Venus. So we like Venus for target practice because it's the only planet with an atmosphere that we can see different phases. Observation we once made of Venus. Carefully you see split in polarization. And every Venus, we create a spectrum. So we cut the Venus up, and for every we split it in polarization in one shot. All the information that we ever want to record about Venus. Also, this we're doing with a crystal device. It's called the polarimetry. So -1. Made a polarization grading that looks like this, kind of strange, and then we built like 9 of these tiles, some polarization, and we again, this was not astronomy, this was an art project at the Amsterdam Central Train Station, where the artist had figured, I just want to project a rainbow. It has to be in the true colors, not just an RGB projection of it, but couldn't make it work, and then he got in touch with us to build this out of the new technology that we had at the time. So this was visible every evening after sundown during 2015, so a real color rainbow at the Amsterdam train station, which was fun. But for us, detecting signs of life, rainbows may be an important step to go there, because rainbows imply liquid water with or without sulfuric acid, which you can see in the polarization signature here in the model of an Earth-like exoplanet in its entirety. So here is the intensity of a planet as a function of its phase angle. Nothing much happens, but in polarization you clearly see this rainbow and signs of Rayleigh scattering, which tells you that there is liquid water. To really find extraterrestrial life, we want to go beyond that. And the holy grail for finding life, at least we know it, is this little bump here, which is a signal of oxygen. And as you know, all the oxygen that we're breathing in here has been produced by forests and algae. If you would wipe out all life on Earth within a couple thousand years, all the oxygen would just be rusted to rot. So finding oxygen in an atmosphere of a planet is really the holy grail. Now, how do we know that when we do this from a ground-based observatory, that we're measuring their oxygen and not our oxygen? There are two redeeming qualities to such a measurement. If their oxygen is Doppler shifted with respect to ours, we know it's theirs. And if their oxygen is polarized, then we know it comes from them. So this is what we're really now basing a lot instrumentation development on. But of course we want to test this. How do we know that this is indeed a sign of life? So colleagues of ours have done this by looking at the Earth in a mirror. So if you're looking at the dark side of the moon, so to say, you see that it's not completely dark, but it has a bit of light, and that's us, that light. So if you analyze that light with a spectral polarimeter, my colleagues have indeed detected life, but then on Earth. So this peak here is a detection of oxygen, and this bump here is a detection of green vegetation. So this is a one-shot observation from the Very Large Telescope. You cannot a big, massive survey with these telescopes. So megalomaniacs as we are, on the moon itself and look back at Earth. Kind of a live Google Earth, but then scientific. So we're building a tiny little instrument that can piggyback on a lunar lander. There's lots of countries, lots of companies going to the moon soon. And let's use these landers to do interesting science. Let's look at Earth and see what a signal of a planet with life looks from a distance. And the moon is ideal because within a month you see the Earth from all these different phase angles. So this by now is our instrument design. So it is really slightly larger than a €2 coin, quite a bit more expensive than a €2 coin though. But it's basically a detector with some non-classical optics on top. There's no more telescope in front of it. We all built everything on the detector. So what we do is that every pixel on the detector has its own wavelength designation and its own polarization designation. We put micro lenses on top, little fish eyes. So every spot you see here is an image of the Earth, and all these spots together build up both the spectral and the polarization information of the Earth. And then we may discover oxygen. But oxygen is still not 100% certainty because there are abiotic processes that could create molecular oxygen. Biologists tell me that there is one biomarker that is really the and it has to do with the fact that complex biology can occur into mirror images. So this is stereochemistry. If they're really just chemistry, like sugar, if you produce sugar in a chemistry lab, you could right-handed sugar. If you have living things like sugar beets and sugarcane producing sugar, it is exclusively right-handed. So this is called homochirality. Biology breaks the symmetry between these two-handedness and picks one. So for instance, all the amino acids involved in biology are all right-handed. But also think of DNA that only twists one way. And it also works like that for chlorophyll. So we built this clunky little instrument to measure the circular polarization, because if you break the symmetry and you have starlight impinging on it, this leaves a trace in circular polarization. So what we did first in the lab is we killed some leaves and we grew some bacteria, and this is the kind of signals that we get. So on the one circular polarization, signal smaller than 1% as a function of wavelength, and you see this very particular wiggle around the wavelength where does its job of photosynthesis. And as the leaf dies, the signal disappears. So we have literally a machine that can see from a distance the difference between life and death. So then we took this out in the field, well first on of the university building with my PhD in Amsterdam, trying to detect life. So we were looking around us. So in the back, you have to know, is kind of the banking district of Amsterdam. So we're looking intelligent life. So, but the first thing we looked at is these beautiful green sports fields there. We figured we got to measure a signal of these sports fields. So we were looking at that, nothing. Completely flat line. So we walked over there, turns out artificial grass. So this was a really good check against false positives, because then we looked at a forest like 3 kilometers down, and we saw this nice wiggle, which is really, we think, the record of detecting life from a distance. And we're about to break this record, because we're now building a version of this instrument that will go to the International Space Station in a couple of years. As you may know, there will be a whole lot of modules around the Columbus module for science. It's called Bartolomeo. So half of these boxes look up to do astronomy, half the boxes look down to do earth science, and we'll occupy a box looking down to do, I guess, both earth science and astronomy. So basically mapping the circular polarization signals for the entire Earth to see what kind of vegetation and algae do to that. It gets a bit crazier than that. This is really my strangest hobby. I collect these beetles. So this picture is taken with the beetles looking at themselves in the mirror, and then photographed through a circular polarizer. And what you see is that all of these beetles go completely dark in the mirror. That means that they're 100% circularly polarized. Moreover, they are all left-handed. So people in the literature, there's a lot of literature on individual species and how they are exactly 100% circularly polarized. Apparently nobody asked the question, why are they all left-handed? And my hypothesis is they're left-handed because of homochirality, and these beetles, they carry the strongest possible signal of a sign of life. So we need to be looking for exoplanets covered in beetles. And to answer that question, I'm now collaborating with the Museum of Natural History in Leiden that has millions of beetles. So we're now doing astronomy-style optical survey of beetles to find out if there's any right-handed beetle, at least on our planet. So I'll keep you updated on that. Then the question is still, how does it come that life on Earth has this imbalance of left and right-handed molecules? There may be a cosmic origin to that, because we know that in around young stars, because of multiple scattering and magnetic alignment of grains, there is locally a surplus of one circular polarization or the other, also in UV. So if the Earth is formed in one of these clumps, it would be irradiated preferentially by one circular polarization over the other, possibly preferentially killing one of the amino acid handedness over the other, thus creating this homochirality. These are observations at large scales. We think we now find a trick to hack the sphere instrument to also observe circular polarization, to start doing these observations at AU scales, and maybe even probe closer to this origin of homochirality and understand in the end fundamentally where life comes from. So for the last 10 minutes or so, that really brings us closer to home with the question, where do we come from, but particularly also how do we sustain life on this planet. So as a spin-off of some of this instrumentation that I've shown you, we now do remote sensing of stuff in our own atmosphere, particularly particulate matter, so small particles that we all ingest. And it's very important to actually do such measurements. I mean, you know pictures like this from very polluted cities. It turns out that just breathing in the air also here takes away a year of your life expectancy. And a lot of measurements are being done on these particles, but it's not completely understood about exactly which particles make it into your bloodstream and stuff like that. So kind of the legal norms are put on so-called PM10. So you suck in air, and all the particles smaller than 10 microns you weigh. But that doesn't tell you much about the smallest particles, the 1 micron particles. They barely contribute to that weight, but it's the smallest particles that you really ingest in your lungs and make it into your bloodstream. It also doesn't distinguish like particles of sea salt that we have a lot in the Netherlands that are completely harmless because you absorb them and you sweat them out, and particles of soot that are harmful to your health. So there's still a lot of information to be added here. There's another good reason to measure particles in the sky. Remember this volcano in Iceland, of which I shall not pronounce the name, because it spewed out this ash cloud. We had to ground all our planes throughout Europe. I was stuck at the Canary Islands back then, so I didn't complain much. But also there, we didn't have the measurements to know where the particles were and how harmful they were. And maybe most importantly, climate change. So there's a lot of stuff that we know about climate change, and I'm pretty sure to this audience I don't have to repeat that. So this graph from the IPCC kind of sums up our current knowledge about climate change, with CO2 here on top. It's clearly in the red, so it warms up our climate, but there's of course an error bar associated with that. Then there's a few other effects that do not contribute much, but look at these. These are the effects of aerosols, so particles in the sky. And look at the error bars associated with them. So particles in the sky can actually cool our climate. They're to the left. This is because they scatter sunlight back into space. Except for when it's soot and it's black and it absorbs this energy. Also, these particles, they create clouds, and clouds in turn also scatter sunlight back into space, but they change completely the precipitation patterns. So to be able to predict what our climate will do exactly, we need to measure the properties of these particles and reduce these error bars, because if you add up these error bars, even quadratically, the total error bar will be larger than the effect of CO2. So they can mask what CO2 has been doing. So as astronomers, we know how to measure dust, right? We know how, if we measure the light scattered of them as a function of wavelength, as a function of polarization, as a function of scattering particle, we can infer with models the amount of particles, the size distribution of these particles, even the chemical composition through the complex index. We can even say something about the shape. So we've been working on developing SPECS, the spectral polarimeter experiment, which of this you see a photo of an early prototype, which was originally meant to go to Mars to measure dust storms there. And what it does is, it's basically, I'm not going to go in detail, it's basically a classic spectrometer for here on out. And in front of this, there's a number of fingers that look in different directions at the same time. And for every direction, we measure polarization. And the way we measure that is very special because we hide the polarization information in the spectrum. So here, for every viewing direction, you get this big sine curve on top of the spectrum. And this is with a few pieces of glass such that when you increase the polarization, the relative amplitude of this sine curve increases. So basically, this measuring up this sine curve tells you in one shot what the polarization is. And if you rotate this polarization contraption, then the phase of the sine curve changes. So in one shot, you get both the degree and angle of polarization. It turns out this is extremely accurate because there's no moving parts, and you get all the information in one shot. So whereas for astronomy we go to nicely high and dry remote desert locations, these kinds of observations we do in the swamp in the Netherlands below sea level, and we wait for blue skies. So this is that satellite prototype. Here's an instrument that we built for the Dutch Environmental Protection Agency, and this is the kind of data that we get. So we detect life. So this little dip here, that's the green bump, that's vegetation, and also this red edge here is vegetation. And we even measure oxygen, right? So for an exoplanet, this would be a detection of life. For measuring air pollution, this will tell you if the pollutant particles are at nose level or if they're several kilometers up. So we've done field campaigns. We now built this in to this aircraft, which you may recognize as a U-2 spy plane, but then painted white by NASA. So this is now flying over California with our instrument to test it for satellite instruments. I think the pilots thought it was cool, and this is the kind of data that we get. So basically, it's a hyperspectral imager where all these different viewing angles go over California, where you see all the different landscape features first in the forward port, and then so all the way to the backward port, together with the polarization. So this has now demonstrated that this technology is really accurate enough. So now we're building this into the next NASA climate satellite called PACE. And just an hour ago, the Dutch government has given green light for constructing this SPECS-1 instrument for the next for this NASA climate satellite PACE. On the American side, there's one little problem that needs to be overcome, and that problem is Orange and sits in the White House. But I'm pretty sure that they can deal with him. So in a couple of years, our technology will be flying on this big Earth observation satellite. So this is spin-off level 1. There's a spin-off of that. We actually put our technology as a joke. We put it on smartphones. So these optics that create this sine curve modulation, we made them out of plastic and put them in front of a smartphone camera, and then we imaged the blue sky, and that seemed to work. So then we got a whole lot of other people observing the same thing. So now we had more than 200,000 of these images in our database because we were measuring ourselves, and we had these national measurement days when finally there was blue sky. We had several thousand citizen scientists armed with our technology and with a special app measure air pollution all together, and that worked spectacularly well. So this was one of these measurement days in July, so no clouds in the sky, and every arrow that you see here is a person doing a measurement. And the direction of the arrow tells you also kind of the time, because you always measure with the sun in your back. So that's why you see these arrows rotate kind of like a clock. The color of every arrow is indicative of the polarization degree of the blue sky, which in turn is indicative of the amount of particles in there. What you also see is that individual measurements are subject to quite some measurement error, which is not due to the few euros of optics that we put in there in plastic. It's because back then we had very limited control over the camera focus. On the right you see the satellite that comes over once a day. But then we took all these measurements and we cleverly co-added them. So you see basically every blue dot is a measurement. So you see that reflecting the population density in the Netherlands, which is kind of nice because in cities where you have air pollution problems, you get more people measuring it and therefore also gaining smaller resolution. You also see a kind of typical gradient of the north of the Netherlands having less stuff in the sky than the south. On this day, this was kind of serendipitous because what we were measuring was smoke from forest fires in Canada 2 weeks prior. So that smoke cloud was drifting over the North Pole and then over the Netherlands, and we were measuring that. So that's why we're also always a bit hesitant in interpreting this in terms of air pollution, because this was at a few kilometers altitude. But it matches nicely with the snapshot of the satellite, and we demonstrated that we have 2 kilometers resolution with this method, whereas the satellite is mostly more like 20 kilometers. So we really add something to the arsenal of other air pollution measurements. So we had another day where we had blue skies again, and you right away see that first of all, a lot of people joined the measurement again. But also all the measurements were way bluer, so less stuff in the air. But if we average again, you see that during the course of the day, now on the left is the morning, on the right is the afternoon, you see these plumes of yellow stuff blowing over the Netherlands, and this is certainly air pollution. Even more so, this is German air pollution. So we could blame you guys. But this really demonstrated that this kind of citizen science network can help in producing scientific knowledge that is important and cannot necessarily be obtained by our professional equipment. So then we had some money to scale this up to selected cities throughout Europe. So you recognize London and Barcelona and Rome. That was a fairly small campaign because then we really ran out of money. And as I said, this started as a joke, so a lot of us did this as a hobby on the side. So then a couple of years ago, I thought the project was dead. Until a year and a half ago, I suddenly got a whole lot of money out of Brussels to develop this again. So now we're developing iSpecs 2.0 that doesn't work just on smartphones that have an Apple logo on the back, but every single smartphone, every single operating system, kind of self-calibrating procedure to deal with all the camera specs. Cameras have gotten better, way better under control, so we're starting to roll this out, not just to measure air pollution, but in this case also we want to measure water quality. So we want to measure the color of water and also do spectroscopy through water. So we're collaborating, for instance, with fishermen in Lake Tanzania, in Tanganyika in Tanzania, to do really relevant citizen science observations for them. So this is a spin-off of a spin-off, and then yet the last layer of spin-off is that with this experience that we had doing science together with thousands of people all across the Netherlands, we got a lot of other scientists asking us, how do we do this citizen science? So to facilitate that, we now establish what a citizen science lab where we challenge scientists, so you guys, to be locked up with at least non-professional scientists. So that can be NGOs, that can be industry, anybody who wants to participate in science to co-develop new kind of citizen science program. We're still looking for nice examples of this citizen science in astronomy that go beyond kind of the classification citizen science that you may know from Galaxy Zoo and stuff like that. So with that, I think our feet are firmly on the ground, and see if the movie of the Earth runs. Yeah, there it is. Thank you for your time.
Thanks very much, Franz, for a wonderful talk. Do we have any questions? Stefan?
Yeah, thank you for the very nice talk. I just noted at the beginning you said you need a 4-meter space telescope. As it happens, we have a 6.5-meter space maybe in the future. So
yeah, so that space telescope, namely Webb, will be awesome, but it doesn't not observe invisible light. So one factor to how close you can look at a star is the diameter. The other factor is the wavelength. In fact, if you divide them by each other, you get the angular resolution. So because Webb only observes in infrared light, its ability to look very close to the star is not as optimized, and also the technology that it carries is not as optimized as a fully dedicated 4-meter telescope at visible light with all the latest technology. So unfortunately we have to wait to the next generation of space telescopes.
Any other questions?
So, thanks for this very nice talk. I have a technical question on the liquid crystals. How do you get them to do what they're supposed to do?
So
how do you prepare them?
Yeah, so liquid crystals come in all kind of different variety. Some of them switch, like the ones in your monitor. In our case, liquid crystal is a bit of a misnomer because they're actually very much solidified on the optic. So our collaborators at North Carolina State University, we can send them any kind of flat glass substrate, and then then I have all kinds of pots of goo. The first pot of goo they throw on, and with a UV laser, they can, and the tunable polarization direction, they can mandate locally in which direction that goo will polymerize. So that will kind of inscribe the pattern that we want. And then additional layers of goo will together, they will all align to this pattern, and together they conspire to be a half-wave retarder for a very broad bandwidth. And that's basically it. I mean, to us, it's a dark art, but basically, we tell them which glass plate to use, which wavelength range, and we send them a phase pattern. It comes out exactly as we want it.
Related to that, so how do you come up with the patterns? Can you elaborate a little bit on it? I guess there's some heavy radiative transfer prediction.
In fact, it is not that heavy. So all you need to do to go from a phase pattern in the pupil to your point spread function is a Fourier transform. So that's not very heavy. It's Fraunhofer propagation. So there are several techniques to, if you know what you want in your point spread function, to optimize the phase pattern. And one of our PhD students, who is also more mathematically inclined, found a way to make sure that the phase pattern that we want is also the mathematical optimal phase pattern that we get. And then we have all kinds of tricks to combine that phase pattern, to multiplex it with all kinds of other stuff that we want to put information on the focal plane. So that's now very much under control as well.
From your talk, I got the impression that you mentioned about 2 or 3 times more big projects than was phases in your group picture. How does that work?
So first of all, we don't like doing very big projects that are millions of euros and run times of decades. So we try to do kind of very targeted little actions. Like for all these ground-based telescopes, most of what we do is just to produce and design this optic. We have it installed, and then we can go have fun with it, trying to observe planets. But yeah, all these people in this group, they have different hats and run these different projects together.
Any further questions? Yep.
One question. What did you motivate all the people to actually put the smartphone in the sky and do the stuff for you?
Yeah. That's a very good question. So first and foremost, because the scientific topic in this case pertain to themselves. Measuring air pollution is important to a lot of people. So we partnered up with the Dutch Astronomical Foundation, for instance. Also because kind of outreach award that enables us to do the project, we got a lot of media exposure. So a lot of people signed in right away. The challenge was that we had developed the app, and all we needed was blue skies. It's probably a bit similar to here, but particularly in the Netherlands, you can wait a long time to get blue skies. So people were getting impatient, and then at some point, our Dutch astronaut and one of the famous weather persons on the TV could announce this day, and it was also a big media spectacle. So people really wanted to be a part of this. But a lot of people kind of got addicted to it, because this IcePex project, to a lot of people, is now associated with nice weather. So there are still people who take this thing along on their vacation, on their bike tour, and then throw measurements on the still. So I think kind of being addicted to doing science, I think that part we got right.
A immediate follow-up on that. How would I get such a thing? I would write to you? Or?
So back then we only got funding to develop an add-on that fit on the iPhone 4 and 5. And if you remember the iPhones, they all had the camera in the kind of the same corner. So with one design, we could reach the most amount of people. But that means also that we had to exclude all the people with Samsungs and other kinds of phones. So, and at some point also the iPhone 5 got out of fashion and we ran out of money, so we stopped the project. Now we got the money to build an add-on with kind of universal interface pieces and also universal calibration. So we're trying to adapt to most of the modern smartphone and also get the community involved in calibrating new smartphones as they come out. So whereas the first time we really did it on the side and this blew up, this time we're taking a bit more time to do the development and then roll out seriously in 1 or 2 years or so.
Any last questions? If not, then can we thank Franz, please?